Okay, so I'll be talking about time, and my name is Krzysztof Dryś. I work at Ingrid, and at Ingrid we are creating software as a service platform which is used by e-commerce shops, and we care about time latencies because this is important for our customers. Our customers are shops, and I will be talking how we approach this time when this is a problem, how we deal with some of the problems, and I also will be talking about latencies. And I will start with some numbers to give you a reference about different time spans. So this is a table which I found on the internet. And as the title says, maybe you have already seen it. And this table says what operations, how much time different operations take. And maybe one or two cache are not that obvious to everyone or branch mispredict. I will get to them in a second. But it's nice to see the scale of this. So, for example, main memory reference is 10 nanoseconds, while sending disk sync is much more, and sending packet between continents is even more. So it's nice to see how all of this how scale, and in a second I will try to rework some of these results. Show them some of these results. But these are numbers which are technical. This is something which happens on the hardware, and this data is a bit old actually, but our user does not care about disk sync. Here is what our end user cares about. This is data from Google again. This is data from the internet again, this time from Google. Not that I found it on Google, it's on the developers.google.com. And it says how user interacting with a web page, what kind of delays they are expecting. So when a user clicks a button, if the result is in 100 milliseconds, its user sees it as immediate. And actually it's not written here, but if the result is under 60 milliseconds, user thinks it was so fast it was unnatural. So this is quite funny, but you can't be too fast. But once you go past 100 milliseconds, user starts to see a delay, and later on you see the more of delay, but you see there is connection between what you clicked and what actually happened. And after 1 second user gets bored, and after 10 seconds user takes a mobile phone and starts looking at the Twitter, and is not interested in your app anymore. I think this is very nice to have this in mind when developing something facing users. Like 1 second is max of what you should do. And there's another piece of advice from Google which says that if you want to go below 100 milliseconds, all your operations should be within 50 milliseconds. And I'm not sure why. It says it's something about event loop in the browser, we should have free time and animations happening, as I understand. But if you want to go within 100 limit, your operations should be within 50 milliseconds. And so this is one, I think, important point, that 50 milliseconds is all the time which you have for operation to be immediate. And another thing which is 5 seconds, which you have for your web page to load on slow connections. So I think these are nice points, thresholds to have in mind, like 100 milliseconds, 1 second, and 5 seconds, and 10 seconds, which is after 10 seconds is much too slow. And I will go back here. I will try now to reproduce some of these results. Let's see how I will do. I will start with branch mispredict because it's my favorite, and it's hard for me to explain because I don't it's fully understand it, and it's a bit like magic. But I will try to explain to you what I understand. So when we think about CPU, which takes tasks and instructions and process them sequentially, you have very old view of CPU. Modern CPUs are different, and if you have like if I is smaller than 5, do something, and else do something, modern CPU can actually concurrently execute condition inside if and one of the branches, and if it's successfully predicted which branch to execute, it's fine. And if it executed incorrect branch because the condition inside if was not as it expected, it will go back to the breakpoint and then execute the second branch. But then you need to pay a price for going back to the breakpoint, and this is branch mispredict. And by the way, this very mechanism, as I understand, was the root for the attack, which was sorry? Meltdown, yeah. This very mechanism was cause for meltdown. And I will try to show it to you, not because this is particularly important when you are developing API, but because this magic is just pure awesome. Okay. So here we go, hopefully. Okay, so I have a test here, but I will erase it because I think it's nicer to start it from start. So I have a sum function which sums numbers, but only big numbers, like numbers which are bigger than half. And you can already see there's room for branch prediction here, right? So I will create a string slice. I already have a function which creates slice, and you need to trust me that it works. And I will do regular. Okay. And this is how you do benchmarks. And okay, I would like to do one more thing. So writing a benchmarks is always a little married for me, because what you need to be, let's say, scared of is compiler optimizations, like compiler seeing that there is no point to execute this sum because it's never actually called. So it would optimize it away and just remove it, but hopefully it won't happen because I added this sync function which just does nothing but accept this argument. Okay, and I won't run it yet. I will create a second slice which is the copy of the first one. So what I do now is I use the syntactic trick to create a copy of fs, and now I will sort it, and okay, let's see what happens. Oh, okay, so you can see the results here. I mean, I hope everyone can see them. So on the sorted slice, this sum function is it's much faster. It's like 6 times faster. Uh, so, hooray to the modern CPUs which make this stuff possible. We use it every day. Probably we shouldn't worry about it too much, but still it's very nice. And maybe let's see how this translates to what we saw. Even let's see if order magnitude is okay. So, I mean, we have here, I always forget, 100,000, array is 100,000. So, I have no idea how it predicts the branch here, but let's assume that half of the branches was mispredicts. So it's 50,000. The difference here is actually it's 400,000. So if we divide it, we get something like 20, right? It's no one can compute it without calculator, right? No, not this, in this area. No, this is age, but I think it's something like this. And here it was. Wow, I have lost it. I think we got one order of magnitude more. I don't know, but I mean it's still very nice to see that it happens. And now I will show you one more thing about L1 and L2 cache reference. And this thing, this is a thing which I mean, I have never ever optimized code for branch mispredict. Maybe it says something about me, maybe it says something about branch misprediction. About L1 and L2 cache, I have optimized code for it once during my studies. So it was not a real code, but still this is something which I did. So L1 and L2 caches are something which are some kind of caches which are employed by your CPU unit. So L1 cache is smaller and it's faster, obviously, and L2 cache is bigger, but it's slower, but it's still faster than the main memory. And now I will try to have show you code which gives this. Okay. I have some tests defined, but I will write test from the start. But let's start with saying what my test will do. What happens here? Okay. What I will try to do here is I will create a table of pointers to maybe I will create a table of pointers to int, and I will create it like this. The whole slice, I mean I will reserve that many slice times offset of memory, and then I will take each element. I mean, so if I take slice len as 10 and offset as 20, I will reserve 10 times 20 of ints, and then I will take pointer to every to 10 elements separated by 20. So what I'm trying to achieve here is to get pointers to int pointing to a different places in memory. Yes, so okay, okay, so if I have some tests defined here, like different lengths and offsets, and I think this is correct. I hope this is correct. So I mean the original slice has size of int bytes, and I mean this is how many bytes takes each element. No, yes, this is how many bytes takes each element, and this is the number of elements. And I will first stop timer because I need to prepare, and then yes, this is it. Test. This is max of element. This is the maximal element which you want to get, and this is offset. And I now start timer because I'm about to start test. And now I will write just regular benchmark. And okay, just give me a second. I forgot if I have a function for this. Okay. Okay, so I will sum just some numbers. So I will sum numbers in the array. This is a pointer. This can go here. I started wrong. Test 3. Okay, as you can see, I'm starting with an array with length of 1000 and offset 1. So this just reserves array of 1000 elements and assigns pointer to each element. And then I increase the size by 2, and then I start giving offsets. Okay, what is interesting is, for example, these two lines. So here we are about to sum the same number of elements. So we take, in each time we are to sum 2000 of elements, but because they are spread here on 12 kilobytes and here on 24 kilobytes, it takes more time. And as I increase how much they are spread, the time increases. And you can see here that as I go from this amount of memory to this amount of memory, the time which takes to sum increases dramatically, even though it seems that number of operations which are performed here is constant. I mean, it takes the array of pointers and just sums the ins this array is pointing to. But because what I believe you are seeing is where first when we have small offset, the items the whole slice can be put into L1 cache. Here it's put into L2 cache sort of, and now it's no longer in L2 cache, it just starts to reference the regular memory. Okay, so this is one thing from the so from this screen here, we took the first 3. I don't know when pizza will arrive, so maybe I will just go down now to sending pings. So to the top, and I will take bottom, and if you have time, I will cover the middle part. So what I did, just for you, is I created instance of Google machine, and this is very nice. I mean, it just took me I'm not paid by Google, sadly. I wish I was, but sorry.
Do you pay them for this?
I mean, not. Am I paying for this? That was the question. I mean, sort of. I mean, each machine should be $7 a month, but I hope. I mean, if I don't forget, I will kill them. I don't know if still you can say this. I will shut them down after the presentation, so the cost should be very small. And I wish. Okay, one thing which I would like to show is. Okay, I have. I hope it's. Oh yeah, sorry, it's in Polish. I have no idea why.
You're Polish.
Yeah. Okay. Yeah, I am Polish, so I should speak Polish. And but I mean, for those of you who aren't speaking Polish, I mean, this UI in Polish is terrible. I really.
Also.
Sorry.
In English also.
Yeah, but in Polish it's even worse. Okay, so just for fun, I created 3 instances. So I'm currently logged to this one. I will pick this one and this one. And this one is Australia. And one thing about Australia is that they have kangaroos, which can be deadly. And the other, I mean, the kangaroos kill. In Australia, spiders haven't killed anyone in a few years. And kangaroos kill people every year, a lot of. So this is one thing about Australia, and the other thing is it's very far away. So you should have this in mind. So I will first, I'm on the first machine, I will ping the, okay, what have happened? I will ping the first machine. But I'm inside the, I hope it will work. So this is what pings are like. Like 200, 1/4 of millisecond. Let's see how it compares to, it's really embarrassing, I can't find it. So we are within this data center, so it's faster. I mean, if you look at this graph, it's half of this half of the score. So nice work, Google. And I mean, I could prepare. I could create instance in CA, but I mean, come on, you see how far is Australia? It takes 1/4 of the second just to ping the instance there. I mean, it's, and it should travel at the speed of light. And okay, I'm done here. I won't speak about Australia anymore. I promise.
We are worried that kangaroos kill packers.
Okay, so what I did so far is that I showed you this table, and if you take away one thing from this talk is you should go to this web address, which will be posted somewhere, hopefully, and look at it, because it's very nice table. And I sort of replicated first 3 results and the last result. And if anyone cares to watch during the pizza, I can try to look at this one and maybe this one. Okay, but this is it. And the other part will be also very nice, but it will be about something a bit different. Yes?
We have still half an hour to pizza, so you...
Yeah, but I have some other stuff to talk about.
I still have a question.
Yes, please.
So if you have time to, can you explain a little more the first example?
The branch mispredict.
Yeah, because there's like missing 2 concepts. I missed like one of them was the latency of the L1 and L2 cache, and the second was the mixed branch prediction.
Yes.
Can you go to this if statement, because there was like if statement
Okay.
greater than half, and yeah, I didn't get.
Okay, so maybe let's do like this. I will try to fit it in 5 minutes, and if we don't make it, we will put it the last thing. Okay, so it's here. Maybe I can make a bit bigger if it helps. Just kidding. Okay, so yeah. So I'm not an expert on this. I just want to make this perfectly clear. But how the traditional view of CPU is that this is one expression which is evaluated, and then basing on this, the CPU makes a jump and either uses a continue or executed this one. This is past. I mean, this is like 90s or even older. No, I mean, I think it was changed in about 2000 here.
Yeah, but the difference between the first test and the second.
Okay, I should have
changing the sorting.
Yeah, okay, I should have said it. Okay, I should have said it, made it clear. Okay, right. And so the difference which we have here is, I'm very glad you asked it, because I mean, I have read it so many times that it was obvious to me, but it's obviously not obvious. So, I mean, when you have random data, you try to make a guess whether this will be false or not. I mean, you are 50-50. You can make it right or make it wrong, and you have no data to base it, previous data to base it on. But when this data is sorted, if you can make a simple prediction, like if the previous, the simple predictor which says if previously I saw this branch and it was executed true, this time it will be also executed true. I mean, this simple predictor will work here. And this is why it works on the, and this is why it's faster on the sorted data. And this thing, this has nothing to do with Go. You will see the same phenomena in Java, in C++, probably not in interpreted languages because they are a bit different, but in a language which executes machine code directly, you will see this kind of phenomena. So I'm not sure on what conditions, but as I see it, the CPU makes a guess that because previously this was true, now it will also be true, and execute this in parallel this and this. And if this turns out to be true, it's happy and we will just go to the next line. And if this turns out to be false, it will go to the breakpoint. I mean, it will somehow roll back before this was executed.
Thank you.
Okay.
Yeah, I think it was enough.
Okay.
As far as I know, it executes two branches simultaneously and compares the result at the end. So it might be a good idea to write else statement that would, for example, subtract from sum and check results then. So there will be two branches.
Okay, so what do you expect to see in this case?
Maybe the same, maybe more closer result.
Closer results. Okay, I mean, I have.
Because I'm just curious.
We can do it. No, I mean
Took longer, but not
yeah, it's a bit closer, but not that much. And I mean, the funny thing about this is it's a bit magic, so it was not that easy to get it. I mean, I needed some time to get this result. For example, if you sort this slice in reverse order, you will not see it.
Yeah, but the question is if you use Mac, so it's the Intel CPU, is the other providers do you have the same results?
I think that as I don't know, as far as I remember, when there was a Spectre was a thing, it was it's true for like your regular CPUs, but it's not true for CPU which you have in your mobile. And this is why, I mean, I'm going now to the area which is very far from what I know, and this is why this CPU, I mean, this CPU can have the same frequency as this one, but still this one will be much faster, because this one have this kind of optimizations. But
ARMs also have some optimizations, but different type. and the Intel one uses general optimization idea from ARM64 architecture. So there could be a difference between 32 and 64 bits as well,
Okay.
and they are both desktop CPUs.
Okay. Okay. I mean, it's more than I know.
Okay,
Honestly.
I have now.
Okay. One more question.
So, yeah, about the second example.
Okay. I mean, it's
when
not.
you were talking about the.
It's yeah, this one.
array. Yeah, so basically this is like a big array, and inside this array there's different
Okay.
big.
Yeah. Okay. So
And
what?
if you are trying to reach to the end of the array, you compute more time. You need to use more time to access the far away
Yes.
data inside this array.
Yeah. So what I do here, I will just rephrase. I'm creating a big array, and I'm taking some subset of it. I'm taking pointers to some subset of it, distributed evenly. So I mean, so even though the data which I actually will be using for my computation is just, let's say, 10 kilobytes, they are spread across 1 megabyte. So they are on a different pages, and I'm not sure I'm using the term page here correctly, but they are in the different memory sectors, and they cannot be fetched into CPU cache at the same time. Okay, I'm very glad you asked this, because I spent so much time preparing this, but it was obvious to me what happens here, and it was not obvious. So I mean, okay, and this is it regarding this part. And we are not doing this kind of optimizations, sadly, but we are not. But we are doing some still, because we usually don't care about that much about milliseconds, but we still want to create fast APIs. And what is fast? And fast can mean different things. So when you have a cron job, fast means that this cron job does not use too many CPU resources because you pay for it. And if it's executed once per hour, you want it to complete within 1 hour, because if it does not complete within 1 hour, we have problems. And if you have a worker which processes events from the PubSub upstream, what you care about is number of events it will process within 1 second. And it's okay to, I mean, this is enough, because if it processes 10 events within a second, it will, you can expect that it will process 600 within a minute. So this rate here is enough. But when you have an API, you cannot describe it with its speed with a single number. What you need is a histogram. And I really hope that everyone has a brief idea what a histogram is. And I will be using a term histogram and percentile, very flexible, let's put it this way. I hope that everyone is okay with this. This is response rates from one of our production services. And it says that, for example, at I'm not sure which hour, but like 10:20, half of the requests were served in 80 milliseconds. 90% of the requests were served in 36 milliseconds, and so on and so on. So it does not say an average rate of response, but it says how many responses, what percent of responses was served at each rate. And why this is preferable to just talking about an average. So take a look at this situation where you have an API which can either always respond in 1 second, let's say exactly, or it can sometimes take a long response and sometimes it's very fast. So in the second, I mean, the average here is the same, but in the second case, I mean, your users won't even start Twitter, they'll make a sandwich waiting for your response. So I mean, this 1 in 1,000 case will be an error, and 1 in 1,000 might not seem that much, but it's, I mean, actually it's quite a lot. If you have a roto, if your hit rate is big. And so the idea from here, I think this is the most important idea, is that when you are creating an NPI, well, you don't care about average response time. What you care is the percentile, and this is a bit the same as you give SLA to your API. So when you sign a contract, you give an SLA that the uptime will be 99.9%. So with this, you translate this to number of days or hours in a year that you should have uptime. So in the same way, you should think about that you will serve 99.9 requests in 1 second, or you can give more nines depending on whether you are Google or not, and whether you have budget for it. But this is not always easy, and I will now say with the problems we've been facing, some of them, and then I will talk about solutions. One of the problems is sequential calls, and I will start with math, maybe not a little math, but it's percentiles and histograms are hard to reason about. So if you have one service which takes an average time to complete in 10 seconds and the other service which has an average time to complete in 20 seconds, you can sum these two numbers and say that these two steps have 30 seconds on average to complete. And this is something which has corresponds to some laws in mathematics, like expected value is cumulative. But if you have two steps which you need to perform, their percentiles don't sum in any obvious way. But you can have some ideas, like if you have 10 sequential steps and all of them are successful almost, but fail 1 in 100 times. So what is the probability that the whole operation will be successful? And this is something which you should be able to compute if you want to graduate from Polish high school, I suppose. But I will give the answer nevertheless. So the probability that each operation is successful is this. So this is approximately 99%. So if you have 10 sequential steps and each of them will succeed each of them can only fail 1 per 1,000 times, the whole operation will fail in 1 per 100 times. And if you replace now fail for slow, you can get the idea that if you have a lot of sequential steps, they don't sum, I mean, they affect overall your percentiles. So critical path is another way of saying sequential steps. I mean, the critical path is the steps which you need to perform to complete the operation, and the long critical path can lead to problems. And I heard it, though I was once I read it and I was unable to retrieve this information, that Amazon.com, for example, allows only one synchronous call on the main web page. So all other calls are optional. And this is what you can do. When you, instead of having 10 operations, which are all required, some of the operations maybe can be optional. So instead of always requiring them, you will support an optional answer if they don't return, or they don't return in fast enough. So this is like a block of code which does this. So we have a synchronous call which can be slow or can fail. We run it in a Go routine. We send an answer from this call to a channel, and then we listen on this channel, and we return the answer from the channel, and if there was no answer within a specified deadline, we will use the context done, and we know that context done will be always returned within 1 second because we do it here. So it should be all nice. And before I go to next slide, I just would like to everyone to look at this, and I was able to put Fura code font onto my LaTeX slide. It took me some time, but I'm very happy about this. Yes, thank you. I mean, you can look at this ligature here, like the arrow was. I mean, come on. This is stuff is important. Okay, but this pattern is very nice, but it has a few problems. Like the default answer is not always obvious. What is this? I mean, it's not always obvious what should be the default answer. And the other thing which is problematic is if here, this context here has already 1 second of deadline, this synchronous call, I mean, this will have no effect. If this context is already like half a second of deadline, this will have no effect. So if, let's say for example that we are on line 2 and we have half a second, we would like this to complete in less than half a second, because after half a second it will be already too late. So making this time here something which is, I mean, 1 second here is probably okay, but something very good is hard to get, because you should have like enough time. You should put here enough time so that you can return the result before the context would be deadline. And the other problem here, this is something which we have experienced heavily in the production, that when your service is under heavy CPU, I mean when your service is using a lot of CPU, relying on this is not reliable. Because I mean this is the best effort promise only, and if you have a lot of CPU, this here will just have no, I mean if you are using a lot of CPU, this here will just not be scheduled to execution. And we saw this happen a lot of times. So this is one thing we should look into, that using this pattern will not save you if, for example, you are not having enough CPU in your service. I'm repeating this myself because I saw this pattern a few times and I'm really, I don't know. I mean, we've been hit hard by this a few times, so this is an important point for me. And another thing which you should care about is calling an external API, which for anyone in this industry is always a problem. I mean, external APIs can just stop working for any reason, and they can start be slow for any reason, and they can stop to obey contracts for any reason. So the API can, which used to return 1 entry, can now return 1 million of entries. And you should probably do something about it, because if you are iterating or downloading the whole content, you can be again very slow. And another funny thing, that even if your service scales very well, an external API which we are calling that might not scale this well. And I'm saying a lot of this because at Ingrid we are integrating with external APIs quite a lot, because we are integrating with external carriers APIs. Yeah, obviously we are not like this, so if you have a plan to integrate with us, just be sure we are fine. And what you can do about this, I mean, you can use defaults and timeouts. So the pattern which I have just showed you before, you can measure response times, and this is answer to most of your troubles. You should measure everything, especially external calls. And maybe you should have an alert which says that if this call is taking twice the normal, and then you should do something about this, if you can. Maybe use a circuit breaker. So circuit breaker is a pattern which says that if call to an external API or to some API failed 10 times, there is no point in calling it 11 times, because it will most probably fail. And this is very important because if you calling an API which is already overloaded, you are putting even more load to it, so giving it a time might help it to recover. And what is very important for us, I mean, what I'm giving here is maybe advice or maybe just what we saw is cache whatever is possible, because, and I will go into caching later. And another point which might break is internal services. And I mean, we are developing microservices, and what I'm seeing more and more that another microservices is just external API, is developed by your colleague, but it still can be flaky. So you maybe should employ the same means of the defense against another microservices that we will employ against external API. We are not doing all of this, but we are constantly improving. And here will be some advice and some things which have helped us so far to fight latencies. Caching. And there are so many benefits of caching. One thing is that you move data closer to yourself. So you saw the pings. You can gain like 10 milliseconds, 100 milliseconds just by being in the same data center rather than calling someone somewhere else. And but what might be even more important is that when you tune your SQL DB or when you tune your Redis, you can put alerts on it. When it's slow, you can scale it as you wish, but you can somehow be sure or more sure that it will respond with the same response times upon different load. And obviously the best idea is to cache everything in memory because it's far fastest. I will show it later, but it's not always possible. It's usually Redis is good enough. And CPU, and this is again something which maybe says something about us, but measuring CPU is hard, and this is something which I read it on the internet, so it must be true. And as I understand it, if you measure it too often, measuring CPU causes pressure on the processor, on the CPU unit, so you can't do it that often. And at least for us, we saw a situation when we are getting metrics using Kubernetes, using Prometheus, and there was a situation where what we saw was surely a CPU spike, but we were unable to catch it using the regular Kubernetes metrics. It might be that it shows that we have something configured wrong, in the wrong way, but probably it also can mean that it's hard to get it very right. And what we saw a few times that even though the graph said that the CPU usage is the service has a lot of free CPU to use, giving it more CPU made the requests much faster. I have yet to learn why it is, but this is what we saw that happened. And this talks about profiling. This is my personal opinion, but it's very strong. I've been programming in Go for, I have like 5 years, and I didn't learn Go to trace. I had a few attempts, but I was on a few talks, but I never did anything meaningful using it. But I did a few meaningful things with Go tool Peprov. And Mateusz, which on 2 months ago did a cool talk about using Go tool Peprov. It's very useful. It's very simple to use. It's much simpler to use. Let's put it this way. It has a nice web UI. It has this flame graph option, which is insanely useful. And what we saw a few times is that we were able to get low-hanging fruits with Go to Peprov. In the situation where trace should have been the first choice, we were still able to optimize something using pprof. And situations which we have caught were too many log writes, where for example we we are logging on debug too much stuff, and marshalling it took too much CPU. Slow marshalling library, even though it should have been fast, but it turned out to be slow, or not enough cached SQL connections. So for example, one situation which we saw was that on a Spike service, on some operation service would do 10 selects from database, and it would start a new connection for each. And what was costly was not the select itself, was cost of the creating connection. So we saw it on the pprof that this was a thing which happened, and we were able to fix it very fast. And when you are creating a microservice, it's very simple. I mean, it's quite simple, I put it this way. Or maybe once you did it once, it's quite simple to have an endpoint which is private on some private port, which allows you to download profiling data. We've been gathering profiling data on production many times, works fine. This is really great stuff. And it's thank you, but we have no pizza, so I still have some stuff to show you. So
Thank you, no thank you.
no, thank you.
Well, with more Australia.
Yeah, okay. My friend was in Australia for half a year, so I know some stuff about Australia. One thing is that my friend told me that they have like big scary spiders which look bad, but they are not poisonous, and they eat the small spiders which are poisonous. So the natural instinct is to be afraid of a bigger spider, but turned out it's not always true. So maybe, do you have any questions about what I have said so far? No. That's probably not good, because the questions so far were very good. Okay, maybe I have prepared some tests. I will just run it, maybe, and because it takes some time. What this test does, it compares time you need to fetch stuff from. Was that fast? No. From memory, from Redis, and from SQL. So what I have here is I create maps of different sizes, and I get one key from them, always the same one. So might be that optimizer is tricking me, but I'm hoping it's not. Then I'm fetching the same key. I'm fetching my local Redis, which hopefully has this key. And I mean, by the way, it's usually a bad idea to do benchmarks on something different than code using this tool, because I think it's a bit stretching it. But I mean, who cares? And then I'm having, no, not who cares, but I mean, it's good enough for my presentation, let's put it this way. And finally, I'm also fetching data by primary key, and I have created, pre-populated 4 tables, each with this number of elements. So for example, here I'm creating table test, and I'm using this size, so I have 4 tables like size test 10, test 1000, and so on, and each of them has the same schema, which is primary key of ID and value, which is string, and it has a different number of elements. So what you can see here is that fetching from memory is so much faster. It's just so much faster, and Redis is about it's 4 times faster than SQL, so it's not that dramatic. So you must ask yourself why you should care about Redis. And this is a nice question actually, because one answer is because everyone does it. The other answer is that it's a very nice thing to put on your CV or to brag with your colleagues about. But I think the actual answer is that what I'm benchmarking here is a condition when I have only one client which repeatedly asks for the same key. And what I believe is true that Redis will use, there's pizza coming probably, so the Redis will have the same response times on different load. I mean, until you hit its CPU limit, it will have more or less the same response time, and it's also much simpler to deploy. I mean, I can deploy Redis image with a very simple schema, a very simple scheme, very simple Kubernetes deployment YAML. But so the Redis is more handles the load in a much better way. For SQL, will not handle that easily. I mean, SQL will use much more CPU because it will access disk and this kind of stuff. Okay, so do we care about mutexes or do we want pizza? Sorry? Okay. So it's everything. Thank you very much.